There's a structure in space so massive it shouldn't exist. According to our best models of how the universe works, finding something this large is like rolling a billion-sided die and landing on the exact number you called. The Huge Large Quasar Group stretches 4 billion light-years across. To put that in perspective, if our Milky Way galaxy were the size of a coin, this structure would span the distance from Earth to Neptune and back 16 times. What makes this discovery particularly unsettling isn't just its size. It's that structures this large violate one of cosmology's most fundamental assumptions, a principle Einstein himself relied on when developing his theory of general relativity. The universe, when viewed at sufficiently large scales, should look essentially the same in all directions. Smooth, uniform, predictable. This 4 billion light-year behemoth challenges that assumption in ways that have astronomers questioning whether we truly understand the universe's architecture at all. But before we dive into why this cosmic giant is rewriting the rules, we need to talk about what quasars actually are. Because calling them bright objects in space is like calling the sun a light in the sky. It's technically accurate, but catastrophically insufficient. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Imagine taking every star in the Milky Way, all 200 billion of them, and concentrating their combined light output into a region smaller than our solar system. That's a quasar. These objects can outshine entire galaxies by factors of 100 or more, pumping out the energy equivalent of 1 trillion suns from a space that light could cross in just days or weeks. The power source? Supermassive black holes. Not the stellar mass variety formed from collapsing stars, but cosmic monsters weighing billions of times more than our sun. As matter spirals toward these gravitational titans, it forms an accretion disk, a swirling maelstrom of superheated gas spinning at significant fractions of light speed. The friction and compression in this disk heat the material to millions of degrees, causing it to radiate across the electromagnetic spectrum with intensity that defies casual comprehension. Here's what makes quasars particularly strange. The nearest one sits 600 million light-years away. That's not because they're rare in our cosmic neighborhood. It's because they don't exist in our cosmic neighborhood anymore. Quasars were most common when the universe was between 2 and 3 billion years old, a period when galaxies collided far more frequently than they do today. Those collisions funneled enormous quantities of gas towards central black holes, igniting them into brilliant beacons visible across cosmic distances. When you observe a quasar, you're seeing the universe's adolescence. The light reaching your telescope left its source billions of years ago, when the cosmos was wilder, denser, more chaotic. These aren't objects in our present universe. They're fossils of cosmic violence, preserved in light that's been traveling since before Earth existed. The term quasar itself comes from quasi-stellar radio source, coined in the 1950s when astronomers first detected mysterious radio emissions from what appeared to be stars. They weren't stars at all, of course. In 1963, Dutch-American astronomer Martin Schmidt examined the spectrum of an object catalogued as 3C273 and recognized something extraordinary. The emission lines he observed were from hydrogen, but they were shifted dramatically toward the red end of the spectrum. not by the small amounts you'd see from a moving star, but by amounts that indicated the object was over 2 billion light-years distant. At that distance, for 3C273 to be visible at all, it had to be radiating with luminosity roughly 4 trillion times that of the Sun. Schmidt had discovered not just a quasar, but evidence of an entirely new class of cosmic phenomenon. Objects so energetic they make normal galaxies look dim by comparison. Since then, we've catalogued hundreds of thousands of quasars. We've found them at redshifts indicating distances of over 13 billion light-years, their light showing us the universe when it was merely 680 million years old. We've measured black holes at their centers with masses exceeding 60 billion suns. We've watched their jets blast matter into intergalactic space at velocities approaching light speed. But individual quasars, however impressive, aren't what's challenging our understanding of cosmic structure. It's how they group together. In 1982, astronomers noticed something peculiar. Quasars weren't distributed randomly across the sky. They clustered, not in small groups of 2 or 3, but in massive assemblies spanning hundreds of millions of light-years. These large quasar groups, or LQGs, represent some of the largest structures we've ever identified in the universe. Think of them as cosmic scaffolding. In the relatively nearby universe, we see galaxies arranged in sheets and filaments, separated by vast voids, like a 3-dimensional spiderweb spanning space. LQGs appear to be precursors to these structures, snapshots of how matter organized itself in the universe's early epochs. For decades, astronomers discovered increasingly large quasar groups, structures 700 million light-years across, then a billion. Each discovery pushed against theoretical limits, but none quite broke them. The cosmological principle, that assumption of large-scale uniformity, held. Calculations based on our understanding of the early universe suggested the largest structures shouldn't exceed about 370 megaparsecs, roughly 1.2 billion light-years. Then Roger Clowes and his team at the University of Central Lancashire started examining data from the Sloan Digital Sky Survey, a comprehensive mapping project that has catalogued millions of celestial objects. In November 2012, they identified something in the vicinity of the constellation Leo, a grouping of 73 quasars. Initial measurements seemed impressive, but not unprecedented. As they refined their analysis over the following 2 months, the true scale emerged. The structure measured approximately 1.24 gigaparsecs in length. That's 4 billion light-years. Its other dimensions weren't much smaller, 640 and 370 megaparsecs. The Huge Large Quasar Group, as it came to be known, was roughly 3 times larger than the theoretical maximum size for cosmic structures. Let me give you a sense of what 4 billion light-years actually means. The Milky Way spans about 100,000 light-years. The distance to our nearest large galactic neighbor, Andromeda, is 2.5 million light-years. The huge LQG is 1,600 times that distance. If you arranged 100 typical galaxies end to end, you wouldn't even approach a tenth of this structure's width. The total mass involved is equally staggering, approximately 6.1 quintillion solar masses. That's 6.1 followed by 18 zeros, times the mass of our Sun. This isn't just matter floating in space. It's organized into 73 distinct quasars, each powered by its own supermassive black hole, each representing a galaxy in the throes of dramatic transformation. The structure sits roughly 9 billion light-years from Earth, placing it at a redshift of 1.27. When the light we're observing left those quasars, the universe was less than 5 billion years old, barely a third of its current age. At that epoch, matter should have been distributed relatively smoothly, with density variations creating structures measured in hundreds of millions of light-years at most. Instead, we find this: a coherent grouping spanning billions of light-years, assembled at a time when the universe supposedly lacked the mechanisms to create such massive structures. It's as if you found a skyscraper in a Bronze Age settlement. The existence alone demands explanation. When Close announced the discovery in January 2013, the scientific response was immediate and divided. Some saw it as a revolutionary finding, potential evidence that our cosmological models were missing crucial elements. Others questioned the methodology, suggesting the grouping might be a statistical artifact rather than a real physical structure. The skepticism wasn't entirely unfounded. Identifying structures in three-dimensional space based on two-dimensional sky surveys and redshift measurements involves sophisticated statistical techniques. You're essentially looking for patterns in how objects cluster, determining whether those patterns are more significant than what random chance would produce. Seshadri Nadatha from the University of Bielefeld published a critical analysis that threw the huge LQG's existence into doubt. Using an expanded map that included all quasars in the region, not just those initially identified by Klaus, Nadatha found the clustering became less pronounced. His analysis suggested the original method could produce thousands of similar groupings, even in completely random distributions, implying the huge LQG might not represent a real structure at all. A 2016 follow-up study added nuance to this debate. Researchers calculated that the probability of finding an LQG as large as or larger than the huge LQG in the surveyed volume was approximately 0.3%. Extremely unlikely, but not impossible. However, when they applied extreme value statistics, accounting for the fact that we'd naturally focus on the largest structure in any given survey, that probability jumped to about 19%. Still notable, but no longer shocking. This is where the story gets genuinely interesting. Because whether the huge LQG is a real bound structure or a statistical mirage, its apparent existence points to something fundamental about how we observe and interpret the universe. Even if these 73 quasars aren't physically connected, even if they're not a coherent structure in the traditional sense, their spatial distribution is telling us something about the conditions in the early universe that we don't fully understand. Why would 73 quasars, scattered across billions of light-years, all switch on within a cosmologically brief period? What mechanism could coordinate quasar activity across such vast distances? The light we're observing from these objects all originated within a relatively narrow time window in cosmic history. Something about the universe at that epoch, something about the distribution of matter or the dynamics of galaxy formation, created conditions favorable for quasar ignition across this enormous volume of space. That's not a coincidence, that's a clue. The cosmological principle that the huge LQG supposedly violates isn't just some arbitrary assumption, it's the foundation of modern cosmology, the bedrock upon which we've built our understanding of the universe's expansion, its age, its composition. Einstein's field equations, which describe how matter and energy curve space-time, assume that at large enough scales, The universe is homogeneous and isotropic, the same everywhere, in all directions. This assumption isn't based on convenience, it's based on observation. The cosmic microwave background, that faint afterglow of the Big Bang, shows temperature variations of only about 1 part in 100,000. The universe, when it was 380,000 years old, was remarkably smooth. As it expanded and cooled, tiny density fluctuations grew under gravity's influence, eventually forming the stars and galaxies we see today. But there are limits to how quickly structures can grow. Gravity works at a finite rate, governed by the speed of light and the expansion of space itself. Calculations based on these constraints suggest maximum structure sizes of around 370 megaparsecs at the epoch we're observing. The huge LQG, if real, exceeds that limit by more than a factor of 3. That's not a minor discrepancy. That's the universe telling us we've misunderstood something fundamental about how cosmic structure forms. Or perhaps we haven't misunderstood anything at all. Perhaps the universe is simply more interesting than our equations suggest. Here's what we know for certain. Quasars aren't evenly distributed across the cosmos like stars sprinkled randomly across the sky. They cluster, they gather in groups. Since 1982, astronomers have recognized that these brilliant beacons tend to congregate in structures called large quasar groups. The huge LQG isn't unique in its existence. It's unique in its scale. Before we discovered the huge LQG, the largest known quasar group stretched across roughly 700 million light-years. Enormous by any measure, but still within the theoretical boundaries imposed by structure formation models. The huge LQG shattered that precedent by a factor of nearly 6 times larger than anything we'd previously observed, 6 times beyond what seemed possible. But why do quasars cluster at all? What invisible architecture organizes them into these cosmic megastructures? The answer lies in the universe's early history, in the primordial density fluctuations that seeded all cosmic structure. When the universe was young, it wasn't perfectly smooth. Quantum fluctuations during the inflationary epoch created tiny variations in density, regions where matter was infinitesimally more concentrated than average. As the universe expanded, gravity amplified these differences. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter to their neighbors, becoming relative voids. Over billions of years, this process carved the universe into a cosmic web. Filaments of dark matter and normal matter stretching across hundreds of millions of light-years, intersecting at nodes where galaxy clusters form. Between these filaments lie vast voids, regions nearly empty of galaxies. The structure resembles neural networks or soap bubbles, a fractal pattern repeating at multiple scales. Quasars inhabit the densest regions of this web. They form where matter concentrates most heavily, where galaxies collide and merge, where supermassive black holes gorge on abundant fuel. A large quasar group, then, represents a particularly dense node in the cosmic web, a region where conditions were ideal for triggering multiple quasars simultaneously. But there's a timeline problem. Quasars don't shine forever. They're temporary phenomena, lasting perhaps 10 to 100 million years in astrophysical terms. Brief compared to the age of galaxies, but long enough to be visible across cosmic distances. For 73 quasars to appear clustered in space, they must also be clustered in time. They must have ignited within a relatively narrow window, Cosmologically speaking, what could synchronize quasar activity across billions of light years? One possibility involves galaxy mergers cascading through the cosmic web. When galaxies collide, they don't simply bounce off each other. They merge, their gravitational interaction funneling gas toward their central black holes. This sudden influx of fuel can trigger a quasar phase. If you have a dense region of the cosmic web where multiple galaxies are interacting simultaneously, you might expect multiple quasars to ignite within the same epoch. But coordinating this across 4 billion light-years requires something more. Some large-scale environmental trigger that affects an entire region of space simultaneously. Perhaps the passage of a particularly massive cosmic filament through the area. Perhaps the gravitational influence of an even larger structure we haven't yet identified. Perhaps something we haven't imagined because we've never observed it before. This brings us back to TON 618. Not part of the huge LQG, but relevant to understanding what makes quasars tick. TON 618 sits approximately 18.2 billion light-years from Earth, though that distance measurement requires some explanation. The light we observe left TON 618 roughly 10.8 billion years ago, when the universe was much younger and smaller. Since then, the expansion of space has stretched the distance between us and TON 618's current location to over 18 billion light-years. We're seeing it as it was, not as it is. What we see is extraordinary. TON 618 shines with a luminosity roughly 140 trillion times greater than our Sun. To put that in perspective, it's brighter than our entire Milky Way galaxy. All 200 to 400 billion stars in our galaxy combined don't match the light output of this single quasar. That light comes from an accretion disk surrounding a supermassive black hole containing between 40.7 and 66 billion solar masses. The Guinness World Records recognizes it as the most massive black hole ever discovered. The mass estimate varies because measuring black hole mass at such distances involves significant uncertainty, but even the lower bound is staggering. Sagittarius A star, the supermassive black hole at the Milky Way's center, contains roughly 4.3 million solar masses. TON 618's black hole is over 15,000 times more massive. The entire mass of every star in our galaxy totals about 64 billion solar masses. TON 618's black hole alone nearly matches that figure. The Schwarzschild radius of this monster, the boundary beyond which nothing can escape its gravity, extends roughly 1,300 astronomical units from its center. That's more than 40 times the distance from our Sun to Neptune. If you replaced our Sun with TON 618's black hole, its event horizon would swallow everything out past Pluto and extend deep into the Kuiper Belt. Surrounding this black hole is a Lyman Alpha Nebula at least 330,000 light-years across, triple the diameter of the Milky Way. This glowing cloud of hydrogen gas, ionized by the quasar's intense radiation, represents material that the black hole is still in the process of consuming, or perhaps material it's blown away through powerful winds and jets. How did such a massive black hole form so early in cosmic history? That's one of the fundamental mysteries driving modern astrophysics. The universe is approximately 13.8 billion years old. TON 618's light has been traveling for 10.8 billion years, meaning we're observing it as it appeared roughly 3 billion years after the Big Bang. At that epoch, the universe was still in its adolescence. The first stars had formed only a few 100 million years earlier. Galaxies were still assembling from smaller proto-galaxies. Growing a 66 billion solar mass black hole in that time frame seems impossible. Black holes grow by consuming matter, and there's a fundamental limit to how quickly they can feed. When matter falls toward a black hole, it heats up and emits radiation. This radiation exerts outward pressure on surrounding material, pushing it away. At some point, the radiation pressure equals the inward pull of gravity, and accretion stops. This balance point is called the Eddington limit. A black hole accreting at the Eddington limit can roughly double its mass every 50 million years. Start with a 100 solar mass black hole formed from the first generation of stars, and you can reach perhaps 10,000 solar masses after 400 million years of continuous Eddington-limited growth, nowhere near the billions of solar masses we observe in early quasars. Something violates our assumptions. Either these black holes started much larger than stellar mass black holes, perhaps forming from direct collapse of massive gas clouds in the early universe, or they somehow exceeded the Eddington limit, accreting matter faster than our models suggest is possible. Recent discoveries suggest both scenarios might occur. In 2024, astronomers identified a quasar with a black hole consuming the equivalent of 1 solar mass per day, 1 entire star's worth of matter every single day. The accretion disk surrounding this black hole spans 7 light-years and resembles a gigantic magnetic storm cell. Temperatures reach 10,000 degrees Celsius. Lightning crackles constantly. Winds blow at speeds that would circle Earth in 1 second. That quasar, containing a black hole between 17 and 19 billion solar masses, is now recognized as the brightest object in the observable universe. It shines 500 trillion times more luminously than our Sun. Maintaining that emission requires consuming a sun's worth of mass daily, suggesting accretion rates far above the theoretical Eddington limit. Then, in 2026, researchers announced an even more puzzling discovery. A quasar from 12 billion years ago, accreting at roughly 13 times the Eddington limit, while simultaneously emitting strong X-rays and producing powerful radio jets. Theoretical models didn't predict this combination should exist. Super-Eddington accretion involves matter falling into the black hole faster than radiation can push it away. This typically happens in chaotic, turbulent conditions where matter doesn't fall smoothly, but in clumps and streams that can slip past the radiation barrier. The process generates enormous heat and light, exactly what we observe in the brightest quasars. But super-Eddington accretion was supposed to be inefficient, messy, and unlikely to produce the organized jets we see in radio-loud quasars. Jets require stable, ordered accretion disks with strong magnetic fields threading through them. The disk needs to rotate smoothly, funneling matter toward the black hole while simultaneously launching material outward along magnetic field lines at nearly the speed of light. Chaos and order together. Rapid feeding and organized outflow simultaneously. The 2026 discovery showed both occurring in the same system, challenging our understanding of how black holes can grow so quickly while maintaining the structures necessary to produce jets. These observations matter for understanding structures like the huge LQG, because they reveal how quasars actually behave versus how we think they should behave. Our theoretical models, elegant as they are, keep encountering reality that doesn't quite fit, black holes that grow too fast, structures that form too large, quasars that shine too brightly. Each anomaly forces us to refine our understanding. Sometimes that means tweaking the models, adjusting parameters, incorporating new physical processes we hadn't considered. Sometimes it means reconsidering fundamental assumptions about how the universe works. The huge LQG exists at this intersection. Either it's a real structure that demands we revise our understanding of how quickly cosmic structure can form, or it's a statistical artifact that reveals biases in how we identify and categorize astronomical objects. Either conclusion teaches us something important, but there's a third possibility that's easy to overlook. Maybe both interpretations are partially correct. Statistical clustering analysis identifies patterns in data. When you have 73 quasars distributed across a particular volume of space, you can calculate whether that distribution is random or shows evidence of clustering. The original analysis found significant clustering. The reanalysis found less significance. Neither proved definitively whether these quasars are physically connected. Physical connection doesn't require direct gravitational binding. The quasars in the huge LQG aren't orbiting each other. They're separated by hundreds of millions of light years, far too distant for their individual gravity to matter. But they might all inhabit the same large-scale structure in the cosmic web, the same massive filament of dark matter stretching across billions of light years. If that's the case, they're connected environmentally rather than gravitationally. They share a cosmic address, residing in the same neighborhood of the universe, even though they're not neighbors in any conventional sense. The mechanism that triggered their quasar phases might be related to their environment, rather than to direct interaction. This distinction matters because it changes what the huge LQG tells us about structure formation. A gravitationally bound structure would indeed challenge the cosmological principle. An environmental correlation wouldn't necessarily violate any fundamental principles, but it would reveal something interesting about how galaxy formation and quasar triggering depend on large-scale cosmic environment. Recent work on quasar environments has revealed surprising diversity. Some ancient quasars sit in incredibly dense regions, surrounded by 50 or more neighboring galaxies. Others appear remarkably isolated, drifting in cosmic voids with only a handful of nearby companions. Same quasar luminosity, same black hole mass, same cosmic epoch, but radically different surroundings. This shouldn't happen according to our models. The earliest quasars should form in the densest regions of the early universe, where matter concentrates most heavily. They need abundant fuel to power their extraordinary luminosity. Isolated quasars in empty regions lack obvious fuel sources. Yet there they are, shining brilliantly, despite having almost nothing nearby to consume. This suggests our understanding of how quasars acquire fuel and sustain their emission is incomplete. Perhaps they're consuming material we can't easily detect. Perhaps they built up massive reservoirs during earlier periods of intense accretion and are now coasting on stored fuel. Perhaps something about the early universe's dynamics allowed quasars to form in regions that later became voids as surrounding matter dispersed. These mysteries compound when we consider structures like the huge LQG. If individual quasars can exist in wildly different environments, what does it mean for 73 of them to appear clustered together? Are they genuinely inhabiting a shared structure? Or are we seeing a chance alignment of objects that aren't actually related? The answer probably lies somewhere in between. Some clustering is real, some is coincidence. The challenge is separating signal from noise, genuine structure from statistical fluctuation. And that brings us to something unexpected about quasars themselves, something that reveals just how strange these objects really are. The energy they produce defies comprehension. When astronomers first identified quasars in the 1950s, they appeared as faint blue dots in radio surveys. Nothing about their appearance suggested anything unusual, just another star-like object emitting radio waves. But those radio waves told a different story. In 1963, Dutch-American astronomer Martin Schmidt examined the spectrum of 3C273, a quasar in the constellation Virgo. The pattern of emission lines looked familiar. Hydrogen, the most abundant element in the universe. But something was wrong. The wavelengths were all shifted toward the red end of the spectrum by 15.8%. That redshift placed 3C273 over 2 billion light-years away. Nothing that distant should be visible from Earth unless it was producing truly staggering amounts of light. Schmidt's calculations revealed that 3C273 was about 100 times more luminous than the brightest galaxies in nearby clusters. The entire luminosity of a giant galaxy, concentrated in a region far smaller than the galaxy itself. This was the moment quasars transformed from curiosities into cosmic mysteries. How could something outshine 100 billion stars while occupying a space smaller than our solar system? The answer lies in the most extreme physics imaginable. At the center of every quasar sits a supermassive black hole, millions or billions of times the mass of our Sun. Matter spiraling toward that black hole forms an accretion disk, a swirling vortex of gas and dust, heated to millions of degrees by friction and gravitational compression. Most quasars have accretion disks ranging from a light hour to a light month in size. That's tiny compared to a galaxy. Our Milky Way stretches 100,000 light-years across. A quasar's accretion disk might be a few light days wide at most. Yet that compact region can produce luminosity 4 trillion times greater than our Sun. It's like a powerhouse the size of a small flashlight producing as much light as all the houses and businesses in the entire Los Angeles basin. The comparison doesn't do it justice. Nothing in our everyday experience prepares us for objects that radiate as much energy per second as 1,000 galaxies from a region 1/1,000,000th the diameter of the host galaxy. Consider TON 618, one of the most luminous quasars ever discovered. This monster sits 18.2 billion light-years away, though the light we see left when the universe was much younger. TON 618's luminosity reaches 140 trillion times that of our Sun. It's brighter than the entire Milky Way galaxy. The black hole powering this extraordinary emission weighs between 40 and 66 billion solar masses. That's 15,300 times more massive than Sagittarius A star, the supermassive black hole at the center of our galaxy. The Schwarzschild radius of TON 618's black hole, the boundary beyond which nothing can escape, extends 1,300 astronomical units from its center. That's more than 40 times the distance from Neptune to the Sun. Light takes over 7 days to cross the diameter of this black hole's event horizon. Surrounding TON 618 is a Lyman Alpha Nebula at least 330,000 light-years across, triple the size of the Milky Way. This glowing cloud of hydrogen gas is ionized by the intense radiation from the quasar, creating a region of space illuminated by energies we can barely comprehend. But TON 618 isn't the current record holder for brightness. In 2024, astronomers using the European Southern Observatory's Very Large Telescope characterized a quasar that shines 500 trillion times brighter than the Sun. This object is now the brightest thing we've ever observed in the universe. The black hole powering it weighs between 17 and 19 billion solar masses and grows by consuming the equivalent of one sun's worth of material every single day. Every day, one entire star's worth of mass falling into the black hole. That growth rate makes it the fastest growing black hole we've ever detected. The accretion disk surrounding this black hole spans 7 light-years and resembles a gigantic magnetic storm cell, with temperatures reaching 10,000 degrees Celsius, lightning crackling through the superheated gas, and winds moving so fast they would circle Earth in 1 second. These aren't gentle breezes. They're outflows moving at significant fractions of light speed, blasting hundreds of solar masses of material into space every year. Which brings us to a paradox that's been bothering astronomers for decades. Quasars should destroy themselves. The radiation pressure from all that energy should push away the very material trying to fall into the black hole. There's actually a theoretical limit called the Eddington limit that describes the maximum luminosity a black hole can sustain through steady accretion. When radiation pressure equals gravitational pull, accretion should stop. The black hole can't grow any faster without violating basic physics. Yet some quasars appear to violate this limit spectacularly. In 2026, an international team discovered a quasar from 12 billion years ago, hosting a supermassive black hole, accreting at roughly 13 times the Eddington limit, while simultaneously emitting strong X-rays and producing powerful radio jets. This combination shouldn't exist according to many theoretical models. Super-Eddington accretion is theoretically possible under special conditions. If the accretion disk is thick enough or geometrically unusual, radiation might escape preferentially in certain directions, rather than pushing uniformly against infalling material. This could allow temporary periods of extremely rapid growth, but sustaining super-Eddington accretion while also powering a jet and emitting strong X-rays. That's unexpected. Jets require organized magnetic fields and stable accretion flow. Super-Eddington accretion implies chaotic, turbulent conditions. These features don't obviously coexist. The discovery suggests our models of black hole growth are missing something important. This matters because it affects how we understand black hole formation in the early universe. Some of the most distant quasars we've observed contain black holes weighing over 1 billion solar masses when the universe was less than 700 million years old. J0313-1806, currently the most distant quasar known, sits 13.1 billion light-years away. Its black hole masses about 1.6 billion suns. The universe was only 680 million years old when this quasar's light began its journey to us. That's a problem. The first stars probably formed around 300 million years after the Big Bang. If you start with a stellar mass black hole of 100 solar masses at that time and let it grow at the maximum theoretical rate, it wouldn't even reach 1 million solar masses by the time the universe was 680 million years old. You need 1 billion solar masses. Where did they come from? One possibility involves starting with a much larger seed. If a giant cloud of gas collapsed directly into a black hole without forming stars first, you might create a seed black hole weighing 1 million solar masses or more. From there, growing to 1 billion solar masses requires less extreme growth rates. These hypothetical direct collapse black holes might form when a massive primordial gas cloud is bathed in intense ultraviolet radiation from nearby stars, preventing the gas from fragmenting and forming stars normally. Instead, the entire cloud collapses into a single supermassive object that shines briefly as an enormous star before dying and leaving behind a black hole. Once born, 1 million solar mass black hole sitting at the center of a developing galaxy has access to abundant fuel. The galaxy's gravity attracts gas and smaller galaxies. The black hole consumes this material, growing steadily. But even this scenario has problems. Direct collapse requires very specific conditions that might not have been common in the early universe. And we still need to explain how some quasars reach super-Eddington accretion rates while others don't. The truth is, we don't fully understand how the first supermassive black holes formed and grew so quickly. What we do know is that quasars fundamentally shaped galaxy evolution. Astronomers now recognize that the energy from quasars acts as the main driver limiting the growth of massive galaxies. When a quasar turns on, its winds push out hundreds of solar masses of material every year. This material would otherwise form new stars. Hubble observations have shown radiation pressure from the vicinity of supermassive black holes, pushing material away from galactic centers at significant fractions of light speed. As these quasar winds sweep across the galaxy's disk, they snowplow into surrounding gas and dust, creating a feedback mechanism that regulates both black hole growth and star formation. This relationship between black holes and their host galaxies appears fundamental. Nearly every massive galaxy contains a supermassive black hole whose mass correlates with the galaxy's total stellar mass and central velocity dispersion. The black hole is tiny compared to the galaxy, like a penny compared to the moon, yet it exerts enormous influence over the galaxy's evolution. Quasars represent the growth phase of these black holes. When galaxies merge, their gas becomes compressed and funneled toward the central supermassive black holes. The black holes grow rapidly, shining as quasars. Eventually, the quasar winds blow away the remaining gas, shutting down both star formation and further black hole growth. The galaxy transitions from an actively star-forming system to a quiescent elliptical galaxy dominated by old red stars. The quasar fades as its fuel supply dwindles. This process explains why quasars were most common between redshifts 2 and 3, when the universe was 2.1 to 3.3 billion years old. At that epoch, the universe was smaller and more crowded. Galaxies collided frequently, triggering quasar activity. Today, quasars are rare. The nearest known quasar sits about 600 million light-years away. Most galaxies have exhausted their supply of easily accessible gas. Their central black holes have grown to their current masses and now sit dormant, occasionally flaring when a star wanders too close and gets torn apart by tidal forces. But here's what makes recent discoveries so puzzling. Astronomers have found dust-shrouded quasars in the early universe that escaped detection until recently. Using the Subaru telescope to identify candidate galaxies and the James Webb Space Telescope to confirm their nature, researchers discovered hidden quasars shining less than 1 billion years after the Big Bang. These obscured quasars are at least twice as common as previously thought. Dust surrounding them absorbs ultraviolet and visible light, re-emitting it as infrared radiation. Earlier surveys missed them because they were optimized to detect unobscured quasars. The NIR-SPEC spectrograph aboard JWST observed 11 of the most luminous galaxies discovered by Subaru between July 2023 and October 2024. 7 showed broad emission lines, the telltale signature of a quasar, confirming they host supermassive black holes consuming surrounding matter while hidden behind veils of dust. This doubles the known population of early quasars and suggests our census of supermassive black hole growth in the first billion years was seriously incomplete. It also raises questions about what else we're missing. How many more obscured quasars lurk in the early universe, invisible to surveys that aren't looking in the right wavelengths? And how does this revised population affect our understanding of structures like the huge LQG? If quasars are twice as common as we thought, does that make large-scale structures of quasars more likely or less likely? Does it strengthen the case for environmental correlations, or does it suggest that any apparent clustering is even more likely to be statistical coincidence? The answers depend on how these obscured quasars distribute themselves across cosmic structures. If they preferentially form in dense environments, they might cluster more strongly than unobscured quasars. If dust obscuration is random, they should follow the same clustering patterns. We don't know yet. The discoveries are too recent. But they remind us that quasars still guard secrets despite decades of study. Every new observation reveals unexpected diversity. Some quasars blast out powerful radio jets. Most don't. Some sit in incredibly dense environments, surrounded by dozens of neighboring galaxies. Others drift in apparent isolation, with almost nothing nearby. Same luminosity, same black hole mass, same cosmic epoch. Radically different surroundings. This diversity challenges our understanding of what triggers quasar activity and how long it lasts. The standard model suggests quasars turn on during galaxy mergers, when gas gets funneled to the central black hole. But isolated quasars lack obvious merger partners. Perhaps they're consuming gas reservoirs built up during earlier periods. Perhaps they're fed by cold streams of gas flowing along cosmic web filaments. Perhaps something about their formation history gave them access to fuel that other galaxies lack. Whatever the explanation, it needs to account for the full range of observed environments, while also explaining structures like the huge LQG. And that's where things get really interesting, because the huge LQG isn't just about whether 73 quasars constitute a real structure. It's about what quasar clustering tells us about the cosmic web itself. The cosmic web, that filamentous structure of dark matter threading through space, shapes where galaxies form and where quasars ignite. Massive concentrations of dark matter create gravitational wells that attract ordinary matter. Gas flows along these filaments, pools in dense nodes, and eventually collapses to form galaxies. The densest nodes become galaxy clusters. Less dense regions become galaxy groups. And in between, vast voids contain almost nothing. Quasars should trace this structure. If they're triggered by galaxy mergers, they should cluster in dense environments where galaxies frequently collide. If they're fed by cold gas streams flowing along filaments, they should align along those filaments. Either way, their distribution maps the underlying cosmic web. The huge LQG sits at a specific cosmic epoch. Redshift 1.27 corresponds to when the universe was about 5 billion years old. At that time, the cosmic web had already developed its basic structure. Dark matter halos had collapsed. Galaxy clusters had formed. But the universe was still more compact than today, making collisions more common and gas flows more vigorous. What makes the huge LQG potentially significant isn't just its size. It's the question of whether such a large, coherent structure should exist at that particular epoch. Computer simulations of cosmic structure formation predict the statistical properties of the cosmic web at different times. How dense are the densest regions? How large are the largest filaments? How empty are the voids? These predictions emerge from running millions of virtual particles forward through billions of years of simulated time, letting gravity do its work. The simulations start with tiny density fluctuations matching those seen in the cosmic microwave background. They evolve those fluctuations using Einstein's gravity plus the expansion of space. They track how dark matter clumps, how gas cools and heats, how galaxies form and merge. The simulations reproduce the cosmic web we observe in galaxy surveys. They match the clustering of galaxies on various scales. They predict the sizes of voids. They forecast how structures grow over time. And they suggest that at redshift 1.27, you shouldn't find a coherent structure stretching 4 billion light-years across. The cosmological principle, the assumption that the universe looks roughly the same everywhere when averaged over large enough scales, provides the foundation for modern cosmology. Einstein's equations for the universe assume this homogeneity. The Big Bang model depends on it. All our predictions about cosmic structure formation rely on it. But large enough scales is where things get tricky. Below a certain scale, the universe is obviously lumpy. Planets, stars, galaxies, clusters. These are local concentrations of matter embedded in mostly empty space. As you zoom out, though, the distribution should smooth out. By the time you're looking at regions hundreds of millions of light-years across, any particular volume should contain roughly the same amount of matter as any other similar volume. The question is, what defines large enough? Calculations based on the cosmological principle suggest structures shouldn't exceed about 370 megaparsecs, roughly 1.2 billion light-years. The huge LQG, at 4 billion light-years, exceeds this limit by more than 3 times. If it's real, Seshadri Nadatha's critique strikes at the heart of that if. His analysis suggests that the friend of friends algorithm used to identify the huge LQG produces false positives. Feed it random data, quasars scattered uniformly with no clustering whatsoever, and it still identifies hundreds of apparent structures similar in size to the huge LQG. This doesn't mean the algorithm is broken. It means it's finding statistical patterns that don't necessarily correspond to physical structures. Imagine tossing pennies randomly onto a floor. Sometimes, just by chance, several pennies land close together. They form a cluster, not because anything made them cluster, but because randomness occasionally produces apparent patterns. The friend of friends algorithm connects quasars within a certain distance. If 3 quasars happen to lie within that distance of each other, they're linked. If a 4th quasar lies within that distance of any of the first 3, it joins the group. Keep extending this chain, and you can build large apparent structures from random distributions. Nadatha's analysis included all quasars in the region. not just the 73 identified as part of the huge LQG. When he looked at the full distribution, the apparent structure became less prominent. It didn't stand out as obviously distinct from surrounding regions. This suggests it might be a statistical fluctuation rather than a gravitationally bound or causally connected structure. But a 2016 study pushed back. Using more sophisticated statistical methods, researchers calculated that the probability of finding a quasar group as large as the huge LQG by chance in the surveyed volume is only about 0.3%. That's low enough to suggest something real might be happening. Then they applied extreme value statistics, a mathematical framework for predicting the largest example of something you'd expect to find in a given sample. If you survey enough of the sky, you should occasionally find unusually large structures just by chance. The question is whether the huge LQG is larger than the largest structure you'd expect from random variation. After this correction, the probability jumped to about 19%. Not overwhelmingly significant, but not easily dismissed either. It's the kind of result that says, maybe real, maybe not. We need more data. So where does that leave us? The huge LQG occupies a frustrating middle ground. It's either the largest known structure in the observable universe at its epoch, challenging our understanding of cosmic structure formation, or it's a statistical mirage, a pattern that emerges from random scatter when you look hard enough. The answer matters because it affects how we interpret quasar clustering more broadly. If large quasar groups are real structures, they tell us something about the environments that trigger quasar activity. They suggest that whatever turns on quasars can operate coherently over enormous scales, perhaps responding to large-scale gas flows or synchronized merger events. But if they're statistical artifacts, they tell us more about our analysis methods than about the universe. They remind us to be skeptical of apparent patterns, to demand rigorous statistical testing, to consider selection effects and observational biases. The diversity in quasar environments complicates this further. Remember those 5 quasars JWST studied, identical in luminosity and black hole mass, separated by similar cosmic distances, yet living in radically different neighborhoods. One surrounded by 50 galaxies, another essentially alone with only 2 neighbors. If quasars form primarily through galaxy mergers, the isolated ones make no sense. Where's the merger partner? Where's the dense environment that should accompany rapid black hole growth? The standard model predicts that massive black holes grow fastest in dense environments, where galaxies collide and gas gets funneled inward. Isolation contradicts this. One possibility is that isolated quasars are consuming gas reservoirs built up during earlier periods. Maybe they went through a merger phase long ago, accumulated a massive gas reservoir, and are now burning through that fuel, even though the merger partner has long since departed or merged completely. Another possibility involves cold gas streams. Computer simulations show that gas can flow along cosmic web filaments, channeling material from large distances directly into galactic centers. These streams bypass the usual mechanisms that heat gas and prevent it from reaching the black hole. If a quasar sits at the intersection of multiple filaments, it might have access to enormous fuel supplies without needing a dense environment. Or perhaps we're missing something fundamental about quasar triggering. Maybe mergers aren't the only mechanism. Maybe instabilities in galactic disks can drive gas inward. may be interactions that don't qualify as full mergers, close passes, tidal disturbances, harassment by multiple neighbors, can activate quasars without leaving obvious signatures. The obscured quasar discoveries add another layer of complexity. If dust-shrouded quasars are twice as common as unobscured ones, our entire census of quasar clustering is biased. We've been mapping only half the population. The other half remained invisible until JWST's infrared vision could penetrate their dusty cocoons. Do obscured quasars cluster differently than unobscured ones? If obscuration correlates with environment, maybe dustier galaxies live in denser regions where gas and dust concentrations are higher, then including them might strengthen the case for structures like the huge LQG. Or if obscuration is random, they might fill in apparent voids, making the distribution more uniform and weakening claims of large-scale structure. We won't know until surveys complete that map, obscured quasars across the same volumes, where we've mapped unobscured ones. JWST can do this, but it takes time. Each deep field requires hours of observation. Building a complete census demands systematic coverage, not just cherry-picking the brightest candidates. Meanwhile, the super-Eddington quasars discovered recently raise their own questions. When a black hole accretes at 13 times the Eddington limit, it's growing so fast that radiation pressure should blow away incoming material. The fact that accretion continues anyway suggests something unusual about the geometry or the magnetic fields or the way material spirals inward. Does super-Eddington accretion happen more often in certain environments? Are these quasars preferentially found in dense regions where gas supplies are abundant, or in isolated regions where gas can flow inward without being disrupted by neighboring galaxies? The sample size is too small to tell yet. Each new discovery reveals unexpected diversity, but also potential patterns. The fastest growing black holes tend to appear in the early universe when gas was denser and more abundant. The most luminous quasars often show signs of recent mergers. Radio-loud quasars, those blasting out powerful jets, seem to prefer certain types of host galaxies, but exceptions exist for every pattern. Isolated radio-loud quasars, faint quasars in dense environments, slowly accreting black holes in gas-rich galaxies that should be feeding them voraciously. The universe refuses to fit neatly into our categories. This brings us back to the fundamental question underlying the huge LQG debate. How much structure is too much structure? At what scale should the universe smooth out into homogeneity? And what does it mean if we find coherent structures exceeding theoretical limits? The cosmological principle isn't just a convenient assumption, it's a testable prediction of general relativity applied to the universe as a whole. Einstein's equations only have simple solutions if the universe is homogeneous and isotropic on large scales. If it's not, if there are giant structures breaking the symmetry, then either our application of general relativity is wrong, or something about the initial conditions or the evolution of structure differs from our models. Finding structures larger than predicted wouldn't necessarily break cosmology. It might just mean we need to refine our predictions. Maybe the transition to homogeneity happens at larger scales than we thought. Maybe certain configurations of the cosmic web can produce temporary large-scale alignments that look like structures but aren't gravitationally bound. Or maybe something about the early universe, some detail of inflation, some property of dark matter, some aspect of how the first density fluctuations formed, creates a bias toward larger structures at certain epochs. The cosmic web has memory. Conditions in the first moments after the Big Bang influenced which regions became dense and which remained sparse. Those primordial patterns could manifest as apparent large-scale structures billions of years later. The huge LQG exists at a specific cosmic time, remember. Redshift 1.27 corresponds to a particular epoch in cosmic history. The universe was about 1/3 its current age. Star formation was near its peak. Galaxies were merging frequently. The cosmic web had mostly formed, but was still evolving rapidly. Perhaps that epoch was special in ways that make large-scale quasar clustering more likely. Perhaps the balance between gas inflow and outflow, between merger rates and gas consumption, between black hole growth and stellar feedback, created conditions where quasars could activate across vast regions simultaneously. Testing this requires comparing quasar clustering at different epochs. Do we see similar structures at redshift 0.5, at redshift 2, or is the huge LQG unique to its particular cosmic moment? The data to answer this exists in survey archives, but analyzing it demands careful attention to selection effects, completeness, and statistical methods. What we're really asking is whether the universe has structure on scales we didn't expect, whether the transition from the lumpy nearby universe to the smooth cosmic microwave background happens gradually or shows unexpected features along the way, whether quasars trace the cosmic web in ways that reveal hidden aspects of structure formation. The answer affects more than just our understanding of quasars. It shapes our understanding of cosmic evolution, dark energy, the growth of black holes, and the fundamental nature of space-time itself. Structure formation is hierarchical. Small fluctuations in the early universe grew into the first stars. Those stars formed the first galaxies. Galaxies merged into clusters. Clusters connected into filaments and walls. Each step followed predictable physics, gravity amplifying initial density variations, dark matter providing scaffolding, ordinary matter following along. But this hierarchy has limits. The cosmological principle demands that beyond a certain scale, the universe smooths out. Individual galaxies are lumpy. Galaxy clusters are lumpy. Even superclusters show structure. But averaged over large enough volumes, everything should look the same. The question is, what scale? Current models suggest homogeneity emerges around 300 to 400 megaparsecs. Structures larger than this shouldn't maintain coherent organization. They might exist as temporary alignments, galaxies happening to line up from our perspective, but not as gravitationally bound or causally connected entities. The huge LQG, if real, exceeds this limit significantly. Its longest dimension reaches 1,200 megaparsecs. That's not a modest overshoot. That's triple the theoretical maximum. This is where the cosmological stakes become clear. Either the structure isn't real, just a statistical artifact or projection effect, or our models need adjustment. Neither option is comfortable. If it's not real, we've invested considerable effort chasing phantom structures. We've misapplied statistical methods to data that seemed straightforward. We've potentially misled the public about a major cosmological discovery. The scientific process worked eventually, catching the error, but the initial announcement had already shaped perceptions. If it is real, we face deeper questions. Why does this structure exist? What conditions in the early universe allowed it to form? Does it represent a rare fluctuation, or are such structures more common than we thought? And most troubling, what does it mean for our cosmological models? if the universe doesn't smooth out where we expected? Let's explore that second possibility more carefully. Assume for a moment the huge LQG exists as a genuine large-scale structure. What would that tell us? First, it would reveal something about the initial conditions of the universe. The density fluctuations imprinted during inflation, those quantum jitters stretched to cosmic scales, would need to include the right wavelengths and amplitudes to seed such massive structures. Current inflationary models predict a specific spectrum of fluctuations. Finding structures larger than predicted might mean tweaking those models. Second, it would inform our understanding of dark matter. The cosmic web forms because dark matter clumps gravitationally, creating potential wells where ordinary matter collects. If dark matter had different properties, different interaction cross-sections, different velocities, different clustering behavior, it might enable larger structures. Third, it would teach us about the timeline of structure formation. Quasars at redshift 1.27 existed when the universe was about 1/3 its current age. That epoch sits between the early universe, when the cosmic microwave background formed, and today. It's a crucial transitional period when the first generation of massive structures were assembling. Finding a coherent quasar group spanning billions of light-years at that epoch suggests structure formation proceeded differently than we modeled. Perhaps gas infall rates were higher. Perhaps merger rates differed. Perhaps feedback mechanisms, the ways quasars and supernovae inject energy into their surroundings, operated under different conditions. Fourth, it would reveal patterns in quasar activation. For 73 quasars to shine simultaneously across such a vast region, something must have triggered their black holes to feed actively at the same cosmic time. Galaxy mergers can activate quasars, but synchronizing mergers across billions of light-years seems improbable unless some larger-scale process was at work. What could that process be? One possibility involves the cosmic web itself. As dark matter filaments grew and intersected, they might have channeled gas flows along preferred directions. Galaxies sitting at filament intersections would receive enhanced gas supplies, potentially triggering coordinated bursts of quasar activity. Another possibility relates to the cosmic expansion history. The universe's expansion rate affects how quickly structures grow. If expansion slowed or accelerated at particular epochs, due to the changing balance between matter and dark energy, it might create windows where large-scale structure formation was favored. A third possibility is more exotic. Perhaps the huge LQG represents a rare cosmic fluctuation, a statistical outlier that formed against the odds. Inflation predicts that quantum fluctuations should produce a range of structure sizes, with larger structures being exponentially rarer. The huge LQG might simply be the largest such fluctuation in our observable universe, unlikely but not impossible. Testing these possibilities requires comparing predictions to observations across multiple scales and epochs. We need to map quasar clustering at different redshifts, looking for similar structures at other cosmic times. We need to model structure formation with different assumptions about dark matter, inflation, and cosmic expansion, seeing which models best match the data. We need to apply consistent statistical methods, avoiding the biases that might create phantom structures. This is ongoing work. New surveys continue mapping the universe with increasing precision. The Sloan Digital Sky Survey has been joined by successors, EBOS, DESI, Euclid, each pushing deeper and wider. These surveys don't just find quasars, they map galaxies, measure redshifts, trace the cosmic web in exquisite detail. As datasets grow, our ability to distinguish real structures from statistical flukes improves. With millions of galaxies mapped instead of thousands, with redshifts measured to higher precision, with three-dimensional positions known more accurately, patterns emerge that were previously hidden. But here's the paradox. The more data we gather, the more we realize how much we don't know. Every answered question spawns new ones. Every resolved mystery reveals deeper puzzles. The huge LQG debate exemplifies this. We discovered an apparent structure that challenged our models. We questioned its reality, applied new statistical methods, debated its significance. Years later, the question remains unresolved. Some analyses support its existence, others dismiss it as artifact. The truth likely sits somewhere between, a real overdensity of quasars perhaps, but not as coherent or as bound as initially thought. What makes this scientifically valuable isn't the definitive answer, it's the process. By pushing our methods to their limits, by challenging our assumptions, by forcing ourselves to justify every step from observation to conclusion, we sharpen our understanding of what we actually know versus what we merely assume. Quasars themselves continue to surprise us. TON 618, that monster we met earlier, represents one extreme. Its black hole masses 66 billion suns. Its accretion disk spans 7 light-years. Its luminosity exceeds 140 trillion suns. It's not part of the huge LQG, sitting at a different redshift, but it demonstrates how extreme quasars can be. Then there's the 2024 discovery of the brightest quasar yet observed, shining 500 trillion times brighter than the Sun. Its black hole devours the equivalent of one sun's mass daily. The accretion disk resembles a gigantic magnetic storm, with temperatures reaching 10,000 degrees Celsius and winds circling Earth in a second. And in early 2026, astronomers found a quasar accreting at 13 times the Eddington limit, the theoretical maximum rate at which a black hole should be able to consume matter without radiation pressure blowing away its fuel supply. This quasar breaks that rule spectacularly while simultaneously emitting strong X-rays and radio jets, a combination theoretical models struggle to explain. Each discovery refines our picture of what quasars can do. Each extreme object pushes the boundaries of our understanding, and collectively, they inform our interpretation of large-scale structures like the huge LQG. Because here's what we're really asking. Can the universe produce structures larger than our models predict? And if so, what does that mean for everything else we think we know? The cosmological principle isn't arbitrary. It emerges from general relativity applied to the universe as a whole. Einstein's equations describe how mass and energy curve spacetime. When you apply those equations to the entire cosmos, assuming homogeneity and isotropy, you get the Friedmann equations, the mathematical foundation of modern cosmology. These equations predict how the universe expands, how structure forms, how dark energy accelerates cosmic expansion. They've been tested countless ways. The cosmic microwave background matches predictions precisely. The abundance of light elements formed in the first minutes after the Big Bang fits perfectly. The large-scale distribution of galaxies follows expected patterns. But the equations only work if the universe is homogeneous at large scales. If it's not, if giant structures like the huge LQG exist and persist, then either we're applying the equations incorrectly, or something about the universe's contents or history differs from our assumptions. This is why the huge LQG matters beyond mere curiosity. It's not just about whether 73 quasars happen to cluster in a particular region. It's about whether the foundational assumptions of cosmology hold up when tested against the universe's largest structures. The answer affects how we interpret dark energy measurements, how we model cosmic expansion, how we project the universe's ultimate fate. If large-scale structure differs from our predictions, the same models that tell us dark energy is accelerating expansion might need revision. That doesn't mean cosmology is wrong. It means it's incomplete. Our models work brilliantly for most of the universe, most of the time. But at the largest scales, at the earliest epochs, in the most extreme environments, they might need refinement. This is how science progresses, not through revolutionary overturns, but through incremental improvements. We find an anomaly, we investigate, we refine our methods, we gather more data, we update our models. Each cycle brings us closer to understanding reality as it actually is, not as we assumed it to be. The huge LQG, whether ultimately confirmed or refuted, has already served this purpose. It forced us to examine our statistical methods. It pushed us to gather better data. It made us question assumptions we'd taken for granted. And it reminded us that the universe still holds surprises, structures and phenomena we haven't yet imagined. As we peer deeper into space and further back in time, we're not just mapping what exists, we're testing the limits of our understanding, probing the boundaries between what we know and what remains unknown. The breakthrough came from an unexpected direction, not from larger telescopes or more sensitive instruments, but from time itself. Astronomers realized they'd been looking at the huge LQG with a fundamental limitation. They were seeing it as it existed 9 billion years ago, frozen in cosmic amber. What if the structure wasn't permanent? What if they were witnessing a temporary alignment, a moment in cosmic history when these quasars happen to shine simultaneously? This possibility emerged from understanding how quasars actually work. Remember, a quasar isn't always a quasar. It's a phase in a galaxy's life, triggered when massive amounts of matter fall into the supermassive black hole at its center. Galaxy mergers often spark this process, dumping enormous quantities of gas and dust toward the central black hole. But here's the crucial detail. Quasars don't stay lit forever. In cosmic terms, they're brief. 10 million years, maybe 100 million. That sounds like an eternity, but it's a blink compared to a galaxy's multi-billion-year lifetime. Most galaxies spend less than 1% of their existence in an active quasar phase. So if you're looking at 73 quasars all shining at the same cosmic moment, you have to ask, why now? What turned them on simultaneously across billions of light years? One explanation involves the cosmic web, that vast network of filaments and voids that structures the universe at the largest scales. Gas flows along these filaments like water through pipes. When multiple galaxies along the same filament experience gas inflow simultaneously, their black holes could activate in concert, creating what appears to be a coherent structure. But there's a timing problem. Light travels at finite speed, so we don't actually see these quasars as they exist simultaneously. We see each one as it existed when its light began the journey to Earth. The nearest quasar's light left when the universe was about 5 billion years old. The farthest departed slightly earlier. We're viewing a structure spread across hundreds of millions of years of cosmic history, compressed into a single snapshot by the geometry of observation. This realization changed how astronomers approach the problem. Instead of asking, "Is this structure real?" they began asking, what physical processes could produce this pattern of activated quasars across this volume of space at this epoch? The answer might lie in how galaxies formed during that particular era. 9 billion years ago, the universe was denser. Galaxies encountered each other more frequently. Merger rates were higher. If a region of space contained a slight overdensity of dark matter, not enough to violate the cosmological principle, but enough to influence local dynamics, galaxies in that region would merge more often. More mergers mean more quasar activations. Not because anything fundamentally different is happening, but because the normal processes occur more frequently. You end up with an apparent structure, not because galaxies are gravitationally bound into a single massive entity, but because they're all responding to the same large-scale environment. This interpretation preserves the cosmological principle while explaining the observations. The universe remains homogeneous at the largest scales, but statistical fluctuations create regions where quasar activity clusters temporally and spatially. Testing this hypothesis required examining other large quasar groups. Astronomers had identified several before the huge LQG. None approached its size, but they shared similar characteristics. Dozens of quasars spanning hundreds of millions of light-years, all active during the same cosmic epoch. What researchers found was revealing. These structures didn't persist. When you looked at the same regions at different redshifts, earlier or later in cosmic history, the coherent clustering disappeared. The quasars were there, but they weren't all active. The structure existed only during a specific window of time. This temporal limitation suggested something important. If large quasar groups were truly gravitationally bound structures, they should persist across cosmic epochs. The quasars might turn off, but the underlying galaxy distribution should remain. Instead, what appeared was more like a wave passing through the cosmic web, a period when environmental conditions favored quasar activation across a particular volume. The James Webb Space Telescope added another layer to this story. Its infrared capabilities let astronomers peer through the dust surrounding distant quasars, revealing previously hidden objects. In 2023 and 2024, JWST observations identified dozens of obscured quasars in the early universe, quasars so dust-shrouded that previous surveys missed them entirely. This discovery had immediate implications for large quasar groups. If half the quasars were invisible to earlier surveys, then structures like the huge LQG might be even more common than thought. Or conversely, the quasars we do see might represent a biased sample, concentrated in dust-poor regions that don't reflect the universe's true large-scale structure. The obscured quasars also revealed something unexpected about quasar environments. Conventional wisdom held that quasars formed in regions of overdense matter, places where galaxy mergers occurred frequently because galaxies were packed closer together. But JWST found ancient quasars in surprisingly empty regions, surrounded by only a handful of neighboring galaxies. This challenged the narrative that quasars required crowded environments. If a quasar could form in relative isolation, then maybe large quasar groups weren't indicating special regions of enhanced density. Maybe they were revealing something else entirely. perhaps large-scale gas flows, or coordinated triggering mechanisms we hadn't yet identified. Meanwhile, the search for even larger structures continued. In the decades since the huge LQG's announcement, astronomers discovered the Hercules Corona Borealis Great Wall, a possible structure of gamma-ray bursts spanning 10 billion light-years. Like the huge LQG, its reality remains debated. Like the huge LQG, it pushes against theoretical limits. The pattern repeats. We find something unexpectedly large. We question whether it's real. We develop better statistical methods. We gather more data. Sometimes the structure holds up. Sometimes it dissolves into noise. But each cycle teaches us something. After the huge LQG controversy, astronomers developed more sophisticated ways to assess structure significance. They created mock universes, computer simulations that generate random distributions of quasars matching the observed number density. Then they ran their clustering algorithms on these simulations, counting how often they produce structures comparable to what they found in real data. This approach revealed something sobering. Many apparent structures emerged from pure randomness. The human brain excels at pattern recognition, sometimes too well. We see faces in clouds, constellations in random star fields, and coherent structures in statistical noise. The original huge LQG analysis used a method that, when applied to random distributions, produced thousands of similar structures. That didn't necessarily mean the huge LQG was random, but it meant the statistical significance was lower than initially claimed. Subsequent analyses using different methods reached different conclusions. Some found the structure significant at the 99% level. Others placed it well within expected fluctuations. The disagreement persisted, not because anyone was wrong, but because defining structure at these scales involves subtle statistical choices. Do you count only quasars within a certain distance of each other? How do you account for redshift uncertainties? Do you apply the friends of friends algorithm, or minimal spanning tree analysis, or some other clustering metric? Each choice produces different results. This methodological ambiguity doesn't invalidate the research. It reflects the genuine difficulty of extracting signal from noise when your sample size is limited and your objects are separated by billions of light years. Consider the fundamental challenge. The observable universe contains perhaps 200 billion galaxies. Only a tiny fraction host active quasars at any given time. Of those, we can only observe the ones bright enough and unobscured enough to appear in our surveys. We're working with a sparse, biased sample of a vast population, trying to determine whether certain patterns represent real physical structures or statistical flukes. It's like trying to map Earth's geography by observing a few hundred randomly selected points. You might notice clusters, several points in mountainous regions, several near coastlines, but determining whether those clusters represent real features or chance alignments requires sophisticated analysis. The huge LQG debate ultimately became a case study in how science handles uncertainty. Not uncertainty about whether observations are accurate. The quasars definitely exist where measurements place them. But uncertainty about interpretation, about what those observations mean for our broader understanding of cosmic structure. This distinction matters. Science often gets portrayed as a march towards certain knowledge, each discovery adding another brick to an edificating edifice of truth. Reality is messier. We have observations we trust, models that work remarkably well, and interpretations that remain provisional. The huge LQG might be a genuine gravitationally bound structure. It might be a temporary clustering produced by correlated quasar activation. It might be a statistical artifact of insufficient data. All three possibilities remain on the table, weighted differently by different researchers based on which evidence they find most compelling. What's not on the table is the idea that we've reached the end of discovery. Whether the huge LQG proves real or illusory, it's already accomplished something valuable. It forced cosmologists to confront the limits of their knowledge, to develop better tools for analyzing large-scale structure, and to think more carefully about what the cosmological principle actually predicts. Because here's what often gets lost in debates about specific structures. The cosmological principle doesn't forbid all inhomogeneity. It doesn't require perfect smoothness. It predicts that when you average over sufficiently large scales, the universe looks the same everywhere. But sufficiently large is where the wiggle room lies. Early calculations suggested that scale was around 370 megaparsecs, but those calculations made assumptions about how structure formed, how matter clumped, how dark energy affected growth. If any of those assumptions need revision, the predicted scale changes. The universe itself doesn't care about our predictions. It simply is what it is. Operating according to physical laws, we're still working to fully understand. The discoveries keep coming, reshaping our understanding with each observation. In 2024, astronomers using the European Southern Observatory's Very Large Telescope characterized a quasar that redefined extremes. Not just bright, not just massive. This object shines 500 trillion times brighter than our Sun, making it the most luminous object ever observed. The black hole powering it weighs between 17 and 19 billion solar masses, consuming the equivalent of one entire sun every single day. One sun. Every day. That accretion rate isn't just remarkable, it fundamentally challenges our models of black hole growth. The accretion disk surrounding this monster stretches 7 light-years across, larger than the distance from our Sun to the nearest star system. Inside that disk, temperatures reach 10,000 degrees Celsius. Lightning storms rage across distances that dwarf our solar system. Winds blow at such ferocious speeds they could circle Earth in 1 second. This discovery matters because it exists. Period. Whether or not it fits our theories about maximum growth rates, about radiation pressure limits, about how quickly matter can spiral into a black hole, the universe doesn't consult our equations before creating such objects. It simply makes them, leaving us to figure out how. Then, in 2026, researchers working with the Subaru telescope found something even stranger. A quasar accreting at 13 times the Eddington limit, while simultaneously producing strong radio jets and bright X-ray emission. That combination shouldn't exist according to many theoretical models. When a black hole feeds that frantically, radiation pressure should blow away surrounding material, suppressing jet formation. When strong jets exist, they should carry away energy that would otherwise emerge as X-rays. Yet there it sits, 12 billion light-years away, violating expectations with casual indifference. These objects force us to rethink super-Eddington accretion. The Eddington limit represents the theoretical maximum rate at which a black hole can steadily consume matter, the point where radiation pressure from infalling material should halt further accretion. Small black holes in our galaxy occasionally exceed this limit during brief outbursts. but supermassive black holes maintaining super-Eddington rates while producing jets. That suggests physics we haven't fully grasped. Perhaps the accretion isn't steady but pulsed, allowing brief periods of extreme feeding. Perhaps magnetic fields channel material in ways that bypass normal radiation pressure constraints. Perhaps the geometry of the accretion flow differs fundamentally from what our models assume. Each possibility opens new research directions, new questions to answer. Meanwhile, the James Webb Space Telescope revolutionized quasar studies in ways that weren't even possible before its launch. Between July 2023 and October 2024, JWST observed 11 luminous galaxies originally identified by Subaru. 7 showed broad emission lines, the telltale signature of active quasars. But these weren't ordinary quasars. They were dust-shrouded, hidden from optical telescopes by thick cocoons of gas and dust. Their discovery doubled estimates of quasar populations in the early universe. All those decades of quasar surveys, all those carefully constructed catalogues, they'd missed half the population. The brightest quasars weren't necessarily the most common. Many had been hiding in plain sight, their light absorbed and re-emitted at infrared wavelengths that earlier instruments couldn't detect effectively. This matters for understanding galaxy evolution. If quasars were twice as common as we thought during the universe's first billion years, their collective impact on surrounding galaxies must have been correspondingly larger. The energy they pumped into their environments, the star formation they triggered or suppressed, the heavy elements they scattered across nascent galaxies, all those influences need recalculation. JWST also revealed something unexpected about quasar environments. Conventional wisdom held that the earliest quasars formed in overdense regions of the universe, places where dark matter concentrations pulled in extra gas and triggered early galaxy formation. More galaxies meant more material for quasar feeding. The prediction seemed straightforward. Ancient quasars should inhabit crowded neighborhoods. Some do. JWST found quasars surrounded by 50 or more neighboring galaxies, exactly as expected. But others sit in apparent voids, isolated except for a handful of faint companions. Same quasar luminosity, same cosmic epoch, same black hole mass, completely different environments. How does that work? How does a supermassive black hole billions of times the Sun's mass form and feed voraciously when surrounded by almost nothing? Where does the material come from? Did these quasars consume everything nearby, creating their own voids? Did they form through different mechanisms than their clustered cousins? Did cosmic variance produce rare, low-density regions that somehow still generated massive black holes? We don't know yet. But the question itself reveals how much remains mysterious about these objects. Step back for perspective. Every quasar discovery over the past 15 years has expanded the boundaries of what we thought possible. Supermassive black holes existing when the universe was only 680 million years old. Quasars accreting at rates that should be physically impossible. Massive structures spanning billions of light years. Hidden populations doubling known quasar numbers. Isolated quasars thriving without obvious fuel sources. Each finding could have broken our cosmological models. Each could have demanded wholesale revision of fundamental physics. Instead, they've refined our understanding, revealing complexity we'd oversimplified, processes we'd underestimated, phenomena we'd never imagined. The huge LQG controversy exemplifies this progression. Whether it represents a real gravitationally bound structure or a statistical artifact, whether it challenges the cosmological principle or confirms it, the debate itself pushed astronomy forward. Better statistical methods, more sophisticated clustering algorithms, deeper surveys, improved theoretical frameworks for structure formation. That's how science advances, not through unbroken chains of certainty, but through provisional conclusions tested against new evidence, revised when necessary, discarded when untenable. The huge LQG might vanish from future textbooks as newer surveys reveal it was never real. Or it might anchor discussions of maximum structure sizes for decades. Either outcome teaches us something valuable. What matters more than resolving any single controversy is maintaining intellectual honesty about uncertainty. We know quasars exist. We know they're powered by supermassive black holes. We know they influence galaxy evolution. We know they trace large-scale structure. Those facts rest on overwhelming evidence, but we don't know exactly how the first supermassive black holes formed. We don't know why quasar activity peaked when the universe was 2 to 3 billion years old, rather than earlier or later. We don't know whether the largest quasar groups represent genuine structures or selection effects. We don't know why some quasars produce powerful jets while others don't. These gaps aren't failures, they're invitations. Every unanswered question guides future research. Every mystery suggests new observations. Every controversy motivates better analysis. The universe doesn't owe us easy answers. It just is what it is, following physical laws we're still learning to read. Quasars themselves will eventually fade. As galaxies mature and merge less frequently, the supply of gas funneling into central black holes diminishes. The violent feeding that powers quasar emission becomes rarer. In the distant future, when the universe has aged beyond 100 billion years, quasars might cease entirely, leaving behind dormant supermassive black holes embedded in ancient elliptical galaxies. But that's trillions of years away. Right now, quasars blaze across cosmic distances, their light carrying information about conditions billions of years ago. Every photon that survives the journey to our telescopes traveled through expanding space, red-shifted by cosmic expansion, occasionally bent by gravitational lensing, sometimes absorbed and re-emitted by intervening gas clouds. Those photons encode stories about black hole masses, accretion rates, jet velocities, surrounding gas compositions, host galaxy properties. Decoding those stories requires sophisticated instruments, careful analysis, and theoretical frameworks that connect observations to physics. Sometimes we succeed brilliantly. Sometimes we realize we're asking the wrong questions. The largest quasars, whether individual objects or grouped structures, serve as laboratories for extreme physics. Nowhere else in the universe can we study matter behaving under such intense gravitational fields, such powerful magnetic forces, such extreme densities and temperatures. Nowhere else do we see energy generation so efficient that a black hole converts infalling mass to radiation with greater efficiency than nuclear fusion. These objects aren't just cosmic curiosities. They're essential pieces of the universe's evolutionary story. The black holes powering quasars helped regulate galaxy growth, enrich the intergalactic medium with heavy elements, ionized hydrogen after the cosmic dark ages, and established the tight relationship between black hole mass and galaxy properties we observe today. Understanding them means understanding ourselves. The atoms in your body were forged in stars, scattered by supernovae, gathered into new solar systems. But the cosmic environment that made our galaxy's formation possible was shaped partly by ancient quasar winds and jets, pushing gas around, triggering star formation in some regions while suppressing it in others. Every quasar discovery adds detail to that picture. Every refined measurement constrains theories. Every unexpected finding reveals assumptions we'd made without realizing it. The process continues indefinitely because the universe contains more complexity than any finite number of observations can fully capture. So when you hear about a quasar larger than 100 galaxies, remember you're hearing about a possible structure spanning 4 billion light-years, containing 73 of the universe's most luminous objects, existing in an epoch when galaxies were still young. Remember that its reality remains debated, that multiple teams analyzing the same data reach different conclusions, that the controversy itself drives better science. Remember also that individual quasars routinely exceed expectations. Black holes with masses equivalent to 66 billion suns, accretion disks larger than solar systems, luminosities outshining entire galaxy clusters. These aren't theoretical constructs. They're observed phenomena, measured and catalogued and studied. The universe makes things larger, more massive, more energetic than our models initially predicted. It always has. Every time we build better instruments and look deeper, we find new extremes. Not because the universe is trying to surprise us, but because reality doesn't constrain itself to human expectations. That's the real lesson from quasar research. Not that any particular structure exists or doesn't exist, but that the cosmos operates at scales and energies that challenge our intuitions. We're pattern-seeking creatures trying to comprehend phenomena billions of light-years away, billions of years ago, involving physical processes we can barely reproduce in laboratories. The remarkable thing isn't that we sometimes get it wrong, it's that we get it right as often as we do. That human beings, confined to one small planet, have figured out what powers quasars, how supermassive black holes grow, why these objects were more common in the past, what role they play in cosmic evolution. We've measured objects so distant their light has traveled for most of cosmic history. We've detected structures so large they span significant fractions of the observable universe. We've identified physical processes operating at energy scales no human technology can replicate. And we've done it all by collecting photons, tiny packets of electromagnetic radiation that somehow carry enough information to reconstruct conditions billions of light-years away. The largest quasars represent extremes of that endeavor. Whether we're discussing individual objects or grouped structures, we're probing the limits of what the universe produces and what we can observe. Those limits keep expanding as technology improves and understanding deepens. What comes next? Larger surveys will map more quasars across more of cosmic history. Better spectrographs will measure their properties with greater precision. Advanced simulations will model structure formation at higher resolution. Next-generation telescopes will peer even further into the past, perhaps finding quasars at redshifts we haven't yet reached. Each advance will answer existing questions and raise new ones. That cycle never ends. The universe doesn't run out of mysteries just because we solve a few. It reveals deeper layers, subtler phenomena, unexpected connections. So the story of the largest quasars isn't finished. It's ongoing, unfolding as you read this. with new papers being published, new data being analyzed, new discoveries waiting in telescope archives. The universe continues evolving according to physical laws, and we continue learning to read its history in the light reaching us from cosmic distances. That's what makes this science rather than mythology. Provisional conclusions held pending better evidence, willingness to revise understanding when observations demand it, recognition that certainty isn't the goal, but rather progressively better approximations of truth. The largest quasars challenge us because they push boundaries. They exist at the edge of what current theory predicts, sometimes exceeding it, always teaching us something about physics at extremes. Whether the huge LQG proves real or illusory, whether new distance records get set next year or next decade, whether quasar studies reveal new physics or confirm existing models, all of it contributes to humanity's expanding comprehension of the cosmos. And that comprehension, incomplete and provisional as it necessarily remains, represents one of our species' most remarkable achievements. Looking at these 73 quasars scattered across 4 billion light-years of space, what strikes you isn't just their scale. It's what they represent about how we explore the universe. Because here's the thing about cosmic mysteries: they rarely resolve cleanly. They don't snap into focus like a photograph developing, revealing some perfect answer we'd been missing. Instead, they evolve. Our understanding shifts, accumulates nuance, incorporates contradictions. The huge LQG might be real. Statistical analyses suggest probabilities ranging from 0.3% to 19%, depending on which methods you trust, which corrections you apply, which assumptions you consider valid. Those numbers don't converge on certainty. They map uncertainty with increasing precision. That's not failure, that's progress. We've learned that quasar clustering exists, but varies dramatically across cosmic epochs. We've discovered that obscured quasars double the population we thought existed, fundamentally changing how we interpret large-scale structure. We've found individual quasars violating theoretical limits on accretion rates, while simultaneously producing features that shouldn't coexist. Each discovery refined the questions, rather than settling them. Consider what we've actually established beyond doubt. Supermassive black holes exist at galactic centers, some weighing tens of billions of solar masses. Quasars powered by these black holes shine with luminosities exceeding entire galaxies. These objects were far more common in the universe's youth, peaking around 2 to 3 billion years after the Big Bang. They cluster non-randomly, tracing the cosmic web's densest regions, and their influence shaped galaxy evolution across cosmic history. None of that remains controversial. The evidence overwhelming, confirmed by multiple independent observations, consistent across different instruments and techniques. What remains uncertain is interpretation. Whether specific groupings constitute genuine structures or statistical artifacts. Whether the cosmological principle holds at scales approaching 4 billion light-years. Whether our models of structure formation need adjustment or just refinement. These questions matter because they probe the boundaries between what we know and what we assume. The cosmological principle, that assumption of large-scale uniformity Einstein relied upon, isn't arbitrary. It emerges from general relativity's requirements for describing the universe mathematically. If it fails at certain scales, the implications ripple through all of cosmology. But fails might be too strong. Perhaps requires modification, captures it better. Perhaps the transition to homogeneity happens more gradually than we thought, with larger structures possible at earlier epochs, before cosmic expansion dilutes them. Perhaps our calculations of maximum structure size made simplifying assumptions that don't quite match reality's complexity. The universe has taught us this lesson repeatedly. When observations challenge theory, the solution usually involves refining the theory rather than discarding it. Newton's gravity didn't become wrong when Einstein developed relativity. It became a special case, an approximation that works brilliantly under most conditions, but needs correction at extremes. Quasar studies might be revealing similar needs for refinement, not overturning cosmology, but revealing subtleties we'd oversimplified. Meanwhile, individual quasars continue rewriting extremes. TON 618, with its 66 billion solar mass black hole, the 2024 discovery shining 500 trillion times brighter than our Sun, the 2026 finding accreting at 13 times the Eddington limit while producing jets. Each pushes boundaries, each demands explanation, each reveals gaps in understanding. Those gaps aren't embarrassments, they're research opportunities. Every unexplained phenomenon guides future observations. Every anomaly suggests new physics to explore. Every contradiction between theory and observation motivates better models. This is how science actually works, removed from simplified narratives of steady progress toward truth. Real science involves provisional conclusions, competing interpretations, unresolved debates that persist for years or decades. The huge LQG controversy exemplifies this. Multiple teams analyzing identical data, reaching different conclusions, publishing contradictory results, all while advancing the field through methodological improvements. Because regardless of whether this specific structure proves real, the debate forced development of better statistical tools, more sophisticated clustering algorithms, deeper theoretical frameworks. That infrastructure persists even if the structure itself dissolves into insignificance. Future researchers inherit improved methods for identifying genuine large-scale structures, distinguishing them from artifacts, assessing statistical significance properly. The James Webb Space Telescope's discoveries of obscured quasars demonstrate how observational capabilities continually reveal previously hidden populations. Every technological advance opens new windows, exposes biases in earlier surveys, forces reinterpretation of existing data. What we know now about quasar populations differs substantially from what we knew a decade ago, and a decade from now our understanding will have shifted again. That's not instability, that's learning. The largest quasars, whether individual objects or grouped structures, serve as probes of extreme physics and cosmic history. They test our understanding at scales and energies impossible to replicate experimentally. They reveal conditions in the early universe when galaxies were still assembling, when supermassive black holes were growing at rates we struggle to explain, when the cosmic web was establishing patterns that persist today. Every photon reaching us from these distant objects carries information encoded in its wavelength, intensity, polarization. Every spectrum reveals chemical compositions, velocities, temperatures, densities. Every observation constrains theoretical models, eliminating possibilities, highlighting promising directions. The universe doesn't care whether we understand it. It simply exists, operating according to physical laws that were established in the first moments after the Big Bang. Our task isn't to force nature into our theoretical frameworks, but to refine those frameworks until they match what nature actually does. Quasars help with that refinement. When we find black holes growing faster than Eddington limits allow, we learn something about accretion physics. When we discover quasars in unexpectedly empty environments, we learn something about fuel supply mechanisms. When we identify possible structures exceeding theoretical size limits, we learn something about cosmic structure formation. Each lesson might be small. Each might require years to decipher fully. But collectively, they build understanding that didn't exist before. The human achievement here deserves recognition. Where biological organisms evolved to navigate African savannas, now comprehending objects billions of light years distant. We've figured out what powers quasars despite never visiting one, never sampling one directly, never doing anything except collecting and analyzing light. The intellectual leap from mysterious radio sources in the 1950s to detailed models of super-Eddington accretion in the 2020s represents extraordinary progress. Yet mysteries remain. How did the first supermassive black holes form so quickly? Why do some quasars produce jets while others don't? What determines quasar lifetimes? How do obscured and unobscured quasars relate? Why do quasar environments vary so dramatically? These questions don't diminish what we've learned. They highlight what we're still learning, what observations we still need, what theories we still need to develop. The frontier of knowledge always recedes as we approach it, revealing new territories to explore. That's the nature of science at its best. Not definitive answers that close inquiry, but progressively better questions that guide future research. The largest quasars, whether the huge LQG or TON 618, or yet undiscovered objects pushing even further extremes, serve that function. They're signposts marking the boundaries of current understanding, inviting us to expand those boundaries through better observations, sharper analysis, deeper thinking. So when you encounter claims about cosmic structures bigger than 100 galaxies, recognize what's actually being claimed. Not that some discrete object literally spans that distance, but that quasars clustered across that volume might represent a coherent large-scale structure. Recognize also that might carries weight. The claim remains contested, the evidence ambiguous, the interpretation uncertain. That uncertainty doesn't make the research worthless. It makes it ongoing. Science in progress rather than science completed. And science in progress, for all its provisional conclusions and unresolved debates, beats the alternative of comfortable ignorance. The universe makes quasars. It makes them in the early cosmos and the nearby universe. It makes them in crowded environments and empty voids. It makes them with jets and without, obscured and exposed, accreting at legal rates and illegal ones. It makes structures that might span billions of light years or might be statistical mirages. Our job isn't to wish these objects behaved more simply. It's to figure out how they actually behave, why they form where they do, what physical processes govern their evolution. That work continues in observatories worldwide, in simulation clusters processing vast data sets, in theoretical papers proposing new mechanisms and testing predictions. The story doesn't end here because stories about cosmic structure never end. They evolve as observations accumulate and understanding deepens. The huge LQG controversy will eventually resolve one way or another, but resolution won't mean conclusion. It'll mean transition to the next question, the next mystery, the next challenge to our cosmological models. That's how it should be. A universe that yielded all its secrets easily wouldn't be worth studying. We're fortunate to inhabit one that demands our best efforts, rewards careful observation, punishes lazy assumptions, and continually reminds us that reality exceeds imagination. The largest quasars exemplify this dynamic. They exist at the intersection of what we know and what we're trying to understand, bright enough to observe across cosmic distances, extreme enough to test theoretical limits, numerous enough to trace large-scale structure, yet rare enough that each discovery matters. They're simultaneously familiar. We know what quasars are, how they work, why they shine, and mysterious. We don't know why these particular quasars activated when they did, whether their clustering indicates genuine structure, how their black holes grew so massive so quickly. Living with that combination of knowledge and uncertainty requires intellectual humility, confidence in what observations establish, skepticism about interpretations that exceed the evidence, willingness to revise understanding when new data demands it. The researchers debating the huge LQG's reality exemplify this balance, committed to rigorous analysis while acknowledging methodological limitations, defending their conclusions while remaining open to alternative interpretations. That's the scientific method functioning as designed. Not infallible, not always fast, but self-correcting over time as evidence accumulates and understanding matures. And the accumulation continues. Right now, surveys are mapping more quasars. Telescopes are collecting more photons. Computers are running more simulations. Researchers are writing more papers. The infrastructure of modern astronomy operates continuously, generating data faster than anyone can fully analyze it, discovering objects faster than theories can explain them. Somewhere in that flood of data might be evidence that definitively resolves the huge LQG status, or evidence of even larger structures, or phenomena we haven't yet imagined because we're not asking the right questions. The universe doesn't reveal its deepest secrets easily. It makes us work for understanding, forces us to develop better tools, demands increasingly sophisticated analysis, but it rewards that effort with insights that transform how we see reality itself. Quasars taught us that supermassive black holes lurk at galactic centers, that these black holes influence galaxy evolution despite being tiny compared to their hosts, that the early universe was wilder, more violent, more energetic than the relatively calm cosmos we inhabit today. That light traveling for billions of years carries information about conditions we can never visit but can still comprehend. The largest quasars, whether individual objects or grouped structures, continue that education. They're teaching us about extremes of physics, about structure formation at cosmic scales, about the universe's evolution across most of its history. They're revealing complexity we'd underestimated, processes we'd oversimplified, phenomena we'd never anticipated. And they're reminding us, with every new discovery, that the cosmos remains largely unexplored. We've mapped a tiny fraction of its volume, observed a narrow slice of its electromagnetic spectrum, studied a brief moment of its multi-billion-year history. What we know, impressive as it is, represents the beginning of understanding rather than its completion. That's cause for excitement rather than frustration. Every unanswered question is an invitation. Every unresolved mystery is an opportunity. Every controversy, like the huge LQG, is a chance to improve methods, gather better data, develop sharper theories. The universe makes structures at every scale, from subatomic particles to galaxy superclusters. It operates according to physical laws that connect quantum mechanics to cosmic expansion, that link the behavior of individual atoms to the evolution of entire galaxies. And somehow, impossibly, we're figuring it out. One observation at a time, one calculation at a time, one insight at a time. The largest quasars are part of that process. They're data points in the ongoing effort to map cosmic structure, understand galaxy evolution, trace the universe's history from its earliest moments to the present. They're also reminders that nature doesn't conform to our expectations, that reality contains surprises, that the universe is under no obligation to make sense according to our current theories. When it doesn't make sense, we have two options. Assume we're observing incorrectly and dismiss anomalies as errors, or assume we're understanding incompletely and treat anomalies as clues. The history of science shows which approach works better. Every major advance came from taking seriously observations that didn't fit. Stellar parallax revealing cosmic distances far larger than anyone expected. Galactic redshifts demonstrating universal expansion. Cosmic microwave background proving the Big Bang. Accelerating expansion pointing to dark energy. Gravitational waves confirming Einstein's century-old prediction. Quasars might be teaching similar lessons about structure formation, about black hole growth, about the limits of our cosmological models. We won't know until we've gathered enough evidence to distinguish genuine anomalies from noise, real structures from statistical artifacts, physics requiring new theories from physics requiring refined calculations. That process takes time, decades sometimes. The huge LQG controversy has already persisted for over a decade with no definitive resolution. It might persist for another decade or longer. That's fine. Better to remain uncertain while gathering evidence than to prematurely declare victory for one interpretation or another. Because the goal isn't winning arguments, it's understanding reality. And reality, being what it is rather than what we wish it were, deserves patient investigation rather than hasty conclusions. The quasars don't care whether we understand them. They're already gone, those specific objects. The light we observe left billions of years ago when the universe was young. What we're seeing is cosmic history, preserved in photons that traveled across expanding space to reach our telescopes. The quasars themselves have long since faded. They're black holes dormant now. Their galaxies evolved into forms we wouldn't recognize. But the light remains, carrying information across cosmic distances, waiting to be collected and analyzed and understood. That's what astronomy offers. Not direct access to distant objects, but indirect evidence encoded in radiation, waiting to be decoded by creatures who evolved the ability to wonder about origins and endings, about structure and scale, about what the universe was and is and will become. We're those creatures, standing on a small planet, collecting photons from objects billions of light years away, trying to comprehend scales that dwarf our experience and energies that exceed our imagination. The remarkable thing isn't that we sometimes get confused, or that debates persist, or that interpretations conflict. The remarkable thing is that we can do this at all, that pattern-seeking primates develop tools sophisticated enough to study the universe's largest structures, that we've learned to extract meaning from data, that we've built theoretical frameworks capable of predicting cosmic behavior. The largest quasars test those frameworks. They probe boundaries, challenge assumptions, reveal where our understanding needs refinement. They're valuable precisely because they're difficult to explain, because they don't fit neatly into existing models, because they force us to think harder about what we actually know versus what we've merely assumed. That's the real story here. Not whether one particular structure exists, but what the process of investigating reveals about how science works, how understanding develops, how knowledge accumulates despite uncertainties and controversies and competing interpretations. The huge LQG matters less as a specific claim than as an example of inquiry at the frontiers of knowledge, where observations strain against theory and both must adapt to accommodate new evidence. This is where science happens, not in settled questions with universally accepted answers, but in contested territories where different researchers weigh evidence differently, where methodological choices affect conclusions, where provisional understanding gives way to deeper comprehension through the grinding process of observation, analysis, debate, and revision. The universe tolerates our confusion with indifference. It existed billions of years before we evolved to study it. It'll exist billions of years after our species vanishes. Our understanding or misunderstanding changes nothing about cosmic structure, about quasar physics, about whether the huge LQG represents a real entity or a statistical ghost. But our understanding changes everything about us. It transforms how we see our place in the cosmos, how we comprehend the forces that shaped our existence, how we think about scale and time, and the processes that created stars and planets, and eventually life. Quasar research contributes to that transformation by revealing extremes we'd never encounter otherwise, by demonstrating physics we can barely reproduce, by showing us what the universe looks like when black holes feed voraciously, and space stretches dramatically, and matter concentrates intensely. The largest quasars, whatever their final status in textbooks decades from now, have already earned their significance through that contribution. They've pushed astronomy to develop better methods, forced cosmology to examine its assumptions, motivated observers to build more sensitive instruments, and theorists to construct more sophisticated models. That legacy persists regardless of whether specific structures prove real or illusory. So the debate continues. New data arrives, analysis refines, understanding evolves, and somewhere in the universe, quasars keep shining, their light-beginning journeys that will take billions of years, carrying information that future observers will eventually collect and study and try to comprehend, continuing the process we've only just begun.